In this segment, I want to talk about heat pumps and heat engines. And so, this chapter is all about energy flow and energy use. And so, we as humans, we use heat to accomplish useful things all the time. And maybe you don't even realize it. So we're going to talk a little bit about first heat engines and then heat pumps. Now, heat engines, you may not have one of these exactly in your house, but you can model a steam engine pretty well as a heat engine. A heat engine is something that takes heat energy, and as that heat energy flows through it, it produces some useful work. So I hope that you've had a chance to view the demo video that I posted of the Stirling engine, and I hope you'll view that before you watch this video, because I think it'll make more sense what we're talking about. So that Stirling engine in the demo video is a heat engine. It just takes thermal energy and it runs on thermal energy. Now, a steam engine can be modeled pretty well as a heat pump also. In that case, the thermal energy comes from burning coal in the firebox, which creates steam, which you run through a piston in order to do work, move the train forward. Honestly, your automobile engine is pretty well modeled as a heat engine as well. In that case, the thermal energy, the heat energy, comes from exploding gases inside your cylinder, right, of your car. And so that exploding gasoline releases thermal energy, and your engine turns that thermal energy into something useful. Kinetic energy going somewhere, potential energy going up a hill, something like that. Okay, so heat engines are everywhere. The model we're going to introduce is an abstraction, but just keep in mind that this is a model for things like your car, things like a steam engine, all kinds of useful devices. After that, we're going to talk about heat pumps, and we'll come back to this when we get there. But a lot of people have heat pumps in their houses to warm their houses. Less common here than in more mild climates farther south. But you certainly have a heat pump in your house if you have a refrigerator. What your refrigerator does is it moves thermal energy from the inside of the refrigerator into your kitchen, right? And so a heat pump is a device that moves thermal energy from a lower temperature to a higher temperature, right? In a previous segment, we stated that heat can spontaneously and will spontaneously flow from high temperature to low temperature, but it will never spontaneously flow from low temperature to high. With a heat pump, we can force heat to flow from the low temperature to the high temperature. That's what a heat pump does. And we can use that for heating or cooling. First off, let's talk about heat engines. So let's take a look at this PowerPoint slide here. This is the basic operation of a heat engine here. We take in some thermal energy from some hot reservoir, we run it through our heat engine, and what comes out? Well, we end up with some work and some waste energy. As we'll talk about in the next segment, you can never design a heat pump that doesn't have some waste energy. So thinking about our car, right? Nobody's ever going to invent a car that makes you go down the road without the engine getting warm. The engine always gets warm, and that is a physical thing that we cannot get around. It's not just engineering that makes the engine get hot. It's just a physical thing that we can't get around. We'll talk more about that, like I said, in the next segment. So thinking about this as energy flow. Energy flows in from the hot reservoir. We steal some of it to do something useful, a little bit of work, and we always exhaust some out. Conservation of energy holds in a heat pump or a heat engine. In this heat engine, we see coming in is QH, and what comes out is some work. So if we take away the work from what comes in, what's left over? QC. So this equation right here is simply conservation of energy. It's not something you necessarily need to memorize. It's just conservation of energy. The total energy in equals the total energy out. Always, always true. Thinking about this steam engine, how this might apply here. Where does QH come from? Well, QH comes from burning the coal. Right, so we absorb some hot energy here from the burning coal or oil. Looks like this might be a steam engine run on oil. So we burn that oil or coal to get our hot reservoir. That's where our energy comes in. The work here is delivered to these wheels, right? So this heat engine does work on the wheels, which makes the train go forward. And we exhaust some cold some heat into what we call the cold reservoir. What is the cold reservoir? In the case of the steam engine, it's just the environment. It's the outside. Right, so everything that isn't the steam engine is the cold reservoir here. And so a lot of that heat escapes out of here. You can imagine the steam is probably very hot. That's a lot of this QC, but also the sides of the engine are very hot. There's heat escaping all around this engine. So the entire outside is our cold reservoir. Okay, so I know a lot of times students look at these, they seem super abstract, but we are modeling a real engine. For the sake, your automobile is probably an internal combustion engine that runs on gasoline. So your hot reservoir is actually those exploding gases inside your cylinder. It's sort of strange, but for a internal combustion engine, the hot reservoir is inside your cylinder where those gases are exploding, right? Those gases then do some work, which makes your car go down the road, but we know that there is some waste heat. The exhaust coming out of your tailpipe is hot, and if it's winter, you turn on your heater and you get hot air blowing out. That's all this QC, which is exhausted to the cold reservoir. So in the case of your car, the cold reservoir is also everything that isn't your car. So this is completely impossible. And again, this has to do with entropy considerations. You can never have a heat engine that takes all of the heat from the hot reservoir and turns it into an equal amount of work. There is always, always, always some waste heat. This is really a statement of the second law of thermodynamics. The second law of thermodynamics is all about entropy and energy use. And again, we'll talk about that a bit more later. It turns out that it's not obvious, but if we could make a heat engine where this was true, then we could also decrease the entropy of the universe. Remember that entropy is a measure of the disorder of the universe, a word I've thrown around a few times but haven't formally defined. Again, we'll come back to this later. The point being that there's always some waste heat. In any real engine, there's always some waste heat. And it's not just a matter of engineering, it's just a physical fact that you cannot get around. The maximum possible efficiency is given by this equation. Notice it depends on the cold temperature and the hot temperature, the temperatures of those two reservoirs. That defines your maximum efficiency. Remember that efficiency is always defined as useful energy out, which in this case, what's our useful energy out? In the case of the heat engine, our useful energy out is simply work. Right? Remember that the efficiency of any engine or system is always the total useful energy out divided by the total energy in. What's our useful energy out for this heat engine? Well, it's work out. Our total energy in is definitely QH. And so this is the actual efficiency of our heat engine. And it just depends on the engineering of our heat engine, exactly what we're doing with it. It depends on maybe what fuel we're using, right? So this is the actual efficiency, and it depends on the actual situation, the actual engine that you've developed. Contrast that with this equation for Emax given in the PowerPoint. This equation for Emax is the very maximum possible efficiency for a heat engine operating between these two temperatures. These two efficiencies will never be the same unless we have an ideal engine that operates with no friction, which nobody's invented that yet. So even with ideal engine, so to be clear, this Emax is not 100%. And it's not 100%, not because engineers haven't figured out a good enough design. No, it's not. The maximum efficiency of a heat engine is not 100% because of physical limitations placed on it by the second law of thermodynamics, which we're going to get to. It's kind of crazy. This Emax here has nothing to do with engineering. This is a physical maximum placed on engines by the second law of thermodynamics. The actual efficiency will be much less than that. Why? Because real engines have friction. Real engines are not ideal designs. There's still room for refinement and better engines of the future. And so this will never equal Emax in reality. Let's do a quick example. At the Geysers geothermal power plant in Northern California, electricity is generated by using the temperature difference between the 15 Celsius surface and the 240 Celsius rock deep underground. What is the maximum possible efficiency? And what happens to the energy that is extracted from steam that is not converted to electricity? Okay, so for this example, we want to use our Emax equation. And so our Emax is equal to 1 minus Tc over Th. Now we have to be careful, right? These need to be absolute temperatures in Kelvin. Every time, they got to be in Kelvin. Okay. So let's just plug in our numbers and see what we get. We get Emax 1 minus Tc is... So notice I have converted these to Kelvin from Celsius by adding 273 to both of them. Let's see what we get when we run our calculator. I ran my calculator and I got 0.438, or about 44%. So it's kind of interesting, right? It's like, this is not really that high of a value. So that means that out of every joule that we extract from this hot underground reservoir, 44% goes to something useful, generating electricity. 66% is just waste heat. So what happens to the energy that's extracted and not converted to electricity? It heats up the environment. There's probably cooling water. There's probably that runs through, and there's probably a real hot pond next to this place, right? So somehow that is just waste heat. That excess, that 66%, it just warms up the atmosphere. Okay, so that was all about heat engine. So recall that heat will spontaneously flow from hot to cold. What a heat engine allows you to do is to take that flow of heat as it goes from hot to cold and steal a little bit to do something useful. We can turn that process around. Heat will never spontaneously flow from cold to hot, but we can use a heat pump to make that happen. But what we need an input of work. We have to put some work in order to make it happen. So that's what the mechanism of a heat pump is. Shown here, here is a little abstract drawing of what a heat pump does. We apply some work, and this work allows us to pump energy from the cold reservoir to the hot reservoir. So, well, heat engines are kind of abstract and you know, the idealized heat engine is best represented by that Stirling engine, which I showed you a demo of. But of course, that's not a very practical design. You know, you can't make a train engine or a car out of a Stirling engine like that, right? So we applied that idea of a heat engine to a steam engine and to an automobile, and it works great. It's a great model for those things, but it's not quite obvious at first glance how the heat engine is the same, is representing your internal combustion engine. However, you have a heat pump in your house. It's in your kitchen. It's your refrigerator. So this is just straight up how your refrigerator works. We have to plug the refrigerator in or it doesn't work. Right? That's where the energy from the wall comes. So the work here is energy from the wall. There's a compressor in your refrigerator that is doing work in order to move energy from the cold to the hot. The cold reservoir is the inside of your refrigerator, and the hot reservoir is your kitchen. So we see that opening your refrigerator door when it's too hot in your kitchen does not cool your kitchen down. It actually warms your kitchen up. We'll do an example to demonstrate how that works a little bit more here in just a second. Your freezer is also a heat pump. In milder climates, people use heat pumps to heat their houses. Some folks in our climate have heat pumps too. It tends to work much better when it's only a little bit colder outside than you want it to be on the inside, as opposed to around here where we have some nights where it's super cold outside. It doesn't work very well in those situations. So in this climate, if you had a heat pump, you'd probably want an auxiliary source of heating for your house also. But heat pumps, they are all around us. It's interesting though, just look at this, right? Conservation of energy still applies. We still have work in plus QC equals QH, right? The total energy in must equal the total energy out. So conservation of energy always applies, right? But notice something here. If we're using this heat pump to heat the inside of our house, well, we not only get the heat in our house that we paid for, but we also get some from outside. So if we think about our definition of efficiency is what you get over what you had to pay for, well, notice you get more than what you had to pay for here, didn't you? Right? So if we think about our classic definition of efficiency, of what you get over what you had to pay for, then this has an efficiency greater than 1, because we get more energy to the hot reservoir than what we paid for from the electric company right here. Right? And even if we're using it to cool our refrigerator, if we're using a heat pump as a refrigerator, well, it's not obvious that it can be the same as this or even bigger, but it can be, right? And so whereas with heat engines, remember, so with heat engines we have this situation where we couldn't make all of this hot energy go into work, right? We always had some waste. And so this has the effect of saying, okay, a heat engine can never be 100% efficient. In other words, the most efficient that a heat pump can be is 1, right? We can never, and we can't even have 1, is less than 1, right? Because we can never have this situation right here. We can never have 100% efficient. We can never have all of our hot energy go into work. There is always some waste heat. Well, we still have 3 streams here, but the point here is either QC, if we're trying to cool something. So if we're using our heat pump as a refrigerator, QC is the point. If we're using our heat pump as a heater, then QH is the point. So, and there's no requirement here that this be less than 1. So, what people do then is they take this standard definition that we have of what you get over what you have to pay for. And in order to still say, well, efficiencies can't be greater than 1, we say this is a little bit different, right? This is a slightly different situation. Let's not call this an efficiency. Let's call this a coefficient of performance. And so this COP stands for coefficient of performance. And it is the same as our idea of efficiency, but this is the value, this is what we call it when applied to refrigerators. So our definition here still works. This is still what you get over what you paid for. But it's a little bit different for refrigerators and heaters, right? So notice here, if I'm using this heat pump as a refrigerator, the point is QC. That's what I get, because I'm trying to make the inside of the refrigerator colder. But if I'm using the heat pump as a heater, then the point is not to cool the outside, the point is to heat the inside. So QH is what I get. So COP for a heater, well, that's QH over W, because W is what I have to pay for. COP for a refrigerator, well, that is QC over W, because what do I get? The point of the refrigerator is to remove heat from the inside of my refrigerator. So, slightly different here, and as a result, we get slightly different values for the maximum possible coefficient of performance. And again, it depends on the difference. It depends on the 2 temperatures, the temperature of the inside and the temperature of the outside. And again, like we had with our efficiency equations, be careful with these. These need to be in Kelvin. So these always need to be absolute temperatures in Kelvin. But again, these are the maximum coefficients of performance given by the second law of thermodynamics. Again, something that we kind of haven't explicitly stated yet because we're kind of building up to it, right? So it turns out that just like the second law of thermodynamics puts a limit on the maximum possible efficiency of a heat engine, so too the second law of thermodynamics places a maximum limit on the coefficient of performance of a refrigerator or a heater, a heat pump. Okay, and again, it depends on whether I'm using it as a refrigerator for cooling or whether I'm using it for heating. Right? And notice the only difference is this thing on top here. Okay, so let's do a quick example about refrigerators. A typical coefficient of performance for a modern freezer is 5. Depends on how cold you have your freezer set and how warm your kitchen is, among other things. Freezing an ice cube requires the removal of thermal energy from the water. So this heat pump is pumping thermal energy from the inside of your freezer to the kitchen. For every joule of thermal energy removed from the water, how many joules of energy do you have to pay the electric company for? Okay, let's remember our definition of the coefficient of performance. What you get over what you have to pay for. Now, with heat pumps, we have to remember that they can be used as refrigerators or heaters, right? So what you get depends on the application. The exact same device can have a different coefficient of performance depending on what you're using it for. So in this case, our coefficient of performance is 5. What do we get? We get 1 joule. And what do we pay for? That's our unknown. And so, really quickly, we can see that what we pay for is, the answer to part A then, is 1/5 of a joule. So that's actually pretty cool, right? We actually get more out than what we paid for, which is, I mean, that's pretty nice. There's not very many devices that work like that, right? A heat engine certainly doesn't work like that. Very few things work like that. Okay, groovy. This shall not be an equal sign. There you go. All right, so B says how many joules of energy are exhausted into your kitchen? Well, let's look back at this diagram of the heat pump. You can see here that conservation of energy tells us that QH equals work in plus QC. That's just conservation of energy, right? The total energy in has to equal the total energy out. Now the question here states, how many joules of energy are exhausted into your kitchen? Well, your kitchen is the hot reservoir, and so we're looking for QH. And so our answer is QH equals the work in, well, that's what we had to pay for. That's 1/5 of a joule, plus my 5 joules that I took out of my freezer. And so how many joules do we exhaust to the kitchen? Well, 5 and 1/5 joules. How about 5.2 joules? There. And so again, like I said a second ago, the same device can be used in different ways. I don't know, are we heating our kitchen? Sure, maybe we are. We certainly are. Is that the point? Yeah, it depends on whether it's the winter or the summer. So we get 5.2 joules into the kitchen. That just heats my kitchen up. That's all it does. That's the answer to part C. It just heats my kitchen up. We don't have to pay for 1/5 of a joule to make that happen. So you can see here why, if you can get away with using a heat pump for a heater, it really is more efficient.